so no presentation needed. You already know who I am. Lars Schneidenbach is my colleague who works also on that. Unfortunately, he didn't make it, but so that's just me. Let's get started. That's the agenda for today. I'm going to talk about what's the problem that we want to address and how we use, in our use case, Redis, that is the backend of our programming model named the data broker. Then we will see some insights of the data broker, like some implementations details. And then finally, we will see how we use Redis cluster on Sierra supercomputer. So we will start talking about what do we mean with workflow, actually. So complex problem can be solved with a workflow of specialty applications. And there are different challenges that developers have to overcome when working on workflows. Of course, the first one is about the data, because in a workflow, application works together to solve some particular problem, and of course they have to talk to each other, and they talk to each other with using data. But data can have different size, can have different types and different formats, and also the frequency that all the applications in the workflow produce data may be different. And of course, the difference is also about how the frequency and the speed, how data are produced and consumed. Also, the access patterns that regards data may be different, depending just not only among workflows, but also among the application within a workflow. So data access can be both offline and online, just within a single workflow. Moreover, producer and consumers can also run at different times. So they can say that they run asynchronously, and they can introduce, of course, different latencies. But it's not only about data, it's also about coordination. So especially if applications run asynchronously. So some application in the workflow can start at a certain point, some other one can start later. And they can have different duration in time and store and load data at different pieces. But something that, of course, we want to make sure that our workflows have with its performance. So we want to exploit all the hardware resources that we have to make sure that our application runs at low latency, that exploits all the bandwidth that we can have in our architecture, and of course that we want the application to scale. But not only that, we also want that in case something happens, some crash or whatever you may imagine, we want that our workflow and the infrastructure that we are running on can guarantee fault tolerance and automatic recovery. So in case some server, some node goes down or something happens, automatically our workflow can recover itself. So what we want to keep considering all those pieces that I've been talking about, and so we've been talking about a kind of set of problems that we want to address, and we want to provide a solution for that is composed by two parts. First part is the data broker that I've introduced you a couple of minutes ago. The data broker is actually a programming model that helps the application to share data, but not only data, but also you can see sharing also commands or whatever the application needs to coordinate among each other. And so we implemented this programming model that shares the data in forms of name tuples that you can see at a very higher level, like key value pairs. And we rely on the concept of namespace, that is a software-based solution to guarantee data isolation. So to group a certain amount of name tuples that you want to share among applications, you can group them into a single namespace. The access pattern is actually like you can have put, read, and get primitives, and also you can guarantee synchronous and asynchronous access. So with these features on the right side, we want to address the first 3 points that we've been talking about at the beginning of the presentation. While to address performance and reliability, we use Redis as a backend, because all the first part on top right, that's the implementation of the data broker programming model, while the runtime is actually use Redis as a backend. So very quickly, this is how the data broker looks like. You can divide it in 3 main parts. At the top part, there's the client library, that is, of course, the one that is exposed to the user. We have, for now, 2 bindings, so you can use it with C or Python API. More have to come in the future. And the system library is the part that is the middle layer between the backend and the end user API. So this is the one that is matching the user command and are implemented on top of the Redis API. The data broker can provide multiple backend storage options. In this case, of course, we're talking about the Redis implementation. We also have the GuestNet implementation. Some special hardware implementation is work in progress, and also we will provide some file system backend that is also a work in progress. This is a open source project, so anyone who wants to just download or contribute on that. Just some other key feature of the data broker, as I've said, we organize the data into namespaces. So every namespace can have multiple tuple stored in it, and every tuple can have, you can see basically it's a key with a set of values. This set of values is actually a list, and so every key can store more than one data having the same key, of course. We provide also synchronous calls, so you can do put, get, and read asynchronously, not just blocking calls. And on top of Redis, we of course implement all the put, read, and get operations, but also the namespace management. And what I call external to the implementation is that it's not really part of the programming model, but is something that we take advantage from Redis, and is the Redis cluster deployment. So, kind of list of, I'm not going to tell you what Redis is, you already know. So why we picked that? So it's cool. So it's easy to use, and it's also a top of DB Engine's ranking. It's lightweight. There's a clear data model, so it's also easy for a user that never seen anything about Redis to just start interacting with it. It's scalable, it's in memory, so it's fast, and it provides easy backup and recovery features. And something that we are also exploring is of course cloud, and Redis is already ready for the cloud. So give me just 1 second, and I want to show you now how we actually use Redis in the runtime of the data broker. So I've prepared a little animation for you. So let's say that our user wants to get some information from Redis using the data broker. So see, we want to get the value, so the answer for the key to the glory question. So what happened is that, so the user types that DBR, so data broker, get the key that he wants, and the command is put into the request work queue. We can divide the runtime into two main pieces: the sender part and the receiver part. From the sender component, what does is to pull requests that are coming from the user space, and of course in parallel it's also checking for some pending requests that might come from some previous requests that the user have done that is cannot be processed as a single query, but it might be divided into multiple steps, so it's a multi-stage operation. So the sender, what does is to check if there are pending requests to be processed or if we can just pull from the user request. So in this case, we are pulling from the user space, and what we do is to check where the key that we are looking for is stored into Redis cluster or into Redis server. We do that by selecting the right connector to connect to and send our request. And we do that just looking at the hash value that the key has, because Redis is storing the values that are stored in the server are hashed and with some hashing algorithm, CRC16, I think, I don't remember, if I remember correctly. And so we can take this information from the key itself. So once we know the key, we can direct the request to the right server. Once we have where we want to do the connection, we prepare the protocol string straight from the Redis syntax. So we're not actually using any client API for that. And so it's a little scary, but it's easy to decode that string. So what we are asking here is to get an answer from Redis. So we do a pop operation. The pop operation is composed by two parts. The first part is the command, in this case pop, and the second one is the key that we want to look for. And so the two number there means that the command has two parts. The first part is a string that is the command, that is lpop in this case, and that the $4 there in this case stands for the length of the command. And the module 1, it's actually the string that we use to pass it to Redis. That is the key that we want to look for, and the $16 is actually the length of the string. So every command that we send to Redis has hit this shape. It can be, in this case, it's pop, can be push or whatever. That's how it looks like. So at this point we have an IP address where we can connect to, and we have also a string. So we can pack everything and send it to the right Redis server. Now the receiver component come into play, and it stays checking whether or not we have something from on the receive buffer. It can be two kind of requests. Can be a multi-stage. So in that case, we have to still process the operation because it's still not complete. So we put it back into the retry queue. Or if it's completed, we just take the answer we have, put into the completion queue, and we give it to the user space. So as I said, we implemented almost everything. Every command that you can do in the data broker, we have the counterpart on as a Redis command. So the main ones are, of course, put, get, and read that are implemented using rpush, lpop, and lindex, respectively. In the case we want to create a namespace when we want to store our data, the create operation is a two-stage operation. The first operation is create the metadata about the namespace, as for instance a name, and we increase the reference count of the clients that are actually connected, because the client that's creating the namespace is actually also connecting to using that. The delete operation is used to delete a namespace from the Redis server cluster that we're using. And so what it has to do is to query Redis to check whether or not the namespace that we want to delete exists or not. And in case it exists, we set this namespace as mark it as deletable. And another command is detach. That is like a four-stage command. So the detach is used by a client that is connected to a namespace in Redis and wants to disconnect from that. So I can issue a detach command. And what we do is to submit a sequence of operations to Redis. The first, of course, is to decrease the reference count about how many clients are connected to the namespace. In case it was the client that is issuing the detach command was the last one, that command will, so at this point we can delete actually the namespace because no one more is connected to that. So we issue more commands to Redis. That is, what we have to do is like to clean up the namespace if some data is still there. So we issue a scan command to Redis to check all the keys that are in the namespace, and then we delete all the keys that are present there. And in case it is just a single server Redis instance, that's done just for one Redis server. But in case of Redis cluster, these commands are issued into all the Redis servers. And at the end, when everything is clean, we delete the metadata and clean up everything. So now we will move on the main track. This is what's our biggest use case for Redis and the data broker. That is actually deploying it on the Sierra supercomputer. The Sierra Center of Excellence is actually close to here. It's like less than 1 hour in Livermore. It's a supercomputer. It's ranked the second fastest supercomputer in the world, based on the latest LIMPAC. And it's used to ensure the safety and reliability and effectiveness of the United States nuclear weapons. If it makes sense to you, take it as it is. It's It's a cluster of IBM Power 9 and NVIDIA Volta is quite big, is more than 4,000 nodes, 4,320 maybe. And every node is two socket now. We have 20 cores per socket, and every thread, every core has four threads per core. So when was at Livermore, there's a team that used the Sierra supercomputer not only for nuclear weapons, but also to do something different. It's been proven that more than 30% of all human cancer are driven by the mutation of one particular families of genes, the RAS family, and this mutation is not yet able to be targeted with known drugs. So what we want to do is also trying to use computer science to try to find potential drugs to target those kind of illness. In this case, the splash workflow is implementing multi-scale and molecular dynamics code that also makes use of machine learning, the big module there. It uses scalable machine learning to select the cell level simulation patches of interest to study at atomic level of detail. That means that it is using this machine learning model is using a custom autoencoder to represent the patches in a latent space, and the similarity among those patches is determined thanks to a Euclidean, it's very hard word, distance in this latent space. And the patches that are more representative are then used for into the molecular dynamics simulation part that is trying to see how the drugs interact on those patches to see whether or not some kind of interaction may be useful or not to target the illness. Of course, I forgot to mention that we're using here the data broker to store the candidate patches for the simulation that can be then retrieved by the other application in the workflow to start the simulations. That was a couple of challenges that we have to address. The first was how to deploy Redis cluster on Sierra supercomputer, because what you have to do is ask for some nodes to the cluster manager. So it's not that just you can grab whatever nodes you want and just deploy your cluster, but you have to prepare some script to ask for nodes, and then once you have all the information that you need about nodes, so IP addresses, ports, or whatever, you can deploy the Redis cluster on those nodes. So you have to launch the Redis cluster command on all of these nodes. And once, of course, you can set all the parameters and features that you want from your Redis cluster. So in our case, especially, we are making sure that we are logging everything, so in case of failures or something, we have a clear view on what's going on. And of course, there are other parameters that you can set, and other than the log files, we also want to store the RDB files. So this is actually like a snapshot of what's stored on Redis cluster, so in case of failure, so that we can restore everything. If one of the other challenges in this case was what happens if a node fails in the cluster reservation that we have. It's not just if Redis fails for some reason, but really if we lose the node that we have been allocated on for some reason. So if we lose a node, what we have to do is actually to like restart everything from scratch. But since we have we are keep storing the RDB files, we can actually at least restore the current state of the sorry of the cluster. What we have to do is just we have to like relaunch Redis cluster and then load the files that we have stored, because doing that it's not possible to create a Redis cluster and assign hash slots if to the Redis cluster if already data are present into the allocation. So we have to first create and then load. So now going to do a little demonstration about how we do that. I say almost Sierra because I cannot use Sierra. I wish I could, but I can't. So we have a smaller little brother of Sierra. We have some nodes that have the same characteristics and we can use. So it's almost Sierra. What we're doing is a little demo with a little piece of code of the ML part, machine learning part, that is creating the patch data and is adding that to the data broker. Then the code is actually, the patches are retrieved to train the machine learning module. So now, assuming the VPN is working, I should be able to connect. Don't look at my password. Okay, so we first start the Python environment because we need to install something and I don't have root accesses there. So we do okay. So what we do now is trying to start a big Redis cluster, and hopefully the LSF cluster manager will give us 10 nodes, and let's see if that happens. So we can go to the data broker. So I want first to show you this. So what we're doing now is like using this script to start a Redis cluster. Now we want to show you the pieces that we need to do to launch it. So I'm not going on all the details, it's too much, too boring. But so what we have to do first is ask for an allocation for nodes. So what we do is ask to in this case, LSF cluster manager to give us a certain number of nodes. What we have to do is to create a little script for that. So we say our job name is Redis cluster, and we want this for a certain amount of time, and we ask for a certain amount of nodes. And once this is just like the little script to ask for some nodes to the cluster manager. Then once we have the nodes allocated, then we can call. We actually call again the same script, but we launch another function here that is actually starting the Redis server on each of the nodes that we have the allocation. So this should be, was in the other direction. Start servers, this one, yeah. So here we are actually adding all the information that we need to start all the Redis servers. In particular, this is the one that helps that makes all the servers start in a way that at some point we can ask Redis to consider them as a single cluster. So we pass some configuration files, and we ask in those 2 lines here to dump the actual content of the Redis instances, and of course also to log something. So let's try. Hopefully. Of course, I don't remember. So we ask for 10 nodes. We want to have a lot of nodes, and we can try to do like 4 Redis servers per node. So at the end, we maybe have 40 servers Redis cluster. So the long part is waiting. Yeah, okay. We have something, we have the nodes. So this is like a to-do thing, like fix this part of the code that the to-do actually is not really working since we still didn't fix it. So this is the long part, because we are actually launching the commands on all the nodes, and it sometimes takes time, long time, sometimes less time. It depends, of course, also on how many nodes you're asking. So, okay, oh, yeah! Okay, we have it. So this is the list of all the Redis servers, and now we are waiting for Redis to create the cluster from all of those nodes. Please. It usually works. Maybe I asked for too much. But in meanwhile, we can take, once we will hopefully have the cluster up and running, we will need at least one IP address and port of any of the server that we have, because we have to connect to the Redis cluster from the data broker. So what we will do at some point maybe is to set up those information that are the server, the IP address for a server, the port of one of those servers that we want to connect to, and the authorization file, because in this case we are, as you can see from all the to-do list, is to we're using a sort of protected Redis cluster, so you need a password to access to it. And the nice thing of both Redis and the data broker is that you don't really have to know all the Redis IP addresses of the server. Oh yeah, okay, we have all the hash slots covered now, so we have our cluster. I was saying something like, oh yes, we just need one IP addresses and one port configuration, and automatically if there's some key stored in some other Redis server, it would be the runtime, both the data broker and Redis itself, that will address the request to the right Redis server. So now we can go back and we go to the demo. So as I've said, we have to set up the it's an error that I always do, put in the dollar there, I don't know why. So do this. Now we do the port. This is actually then something little bit. Oh, I don't. Oh, this one 10 10 3 4. Okay. We've changed this syntax a little bit. Now everything is just one line, but I'm using a previous older version of the data broker interface. So now what we need also, I need to do this also for the Python environment. And now we need the out file. There it is. I don't know if it's here or not. It is. Here it is out. Okay. Redis. Okay. So we might be good to go and launch the code. I did something wrong, of course. I might have spelled wrong. Let's see if at least this information are okay. Looks like the port is wrong.
What I'm going to walk you guys through, and you're welcome to follow along for this session or later on today, is I'm going to show you how to do HA Redis using a cloud-native storage solution. So one of the first things we're going to do is kind of
If you see something wrong that I don't see, please tell me. Oh, okay.
but the idea behind this demo is essentially
We got it. I might have had something in my bash environment. So we might be good to go.
and then essentially we're going to just walk you guys through the demo itself. So the first thing you do is
Okay, we got it. We have. This is always nice to read. So now what it's doing is creating some patches of the simulation and put it into the data broker, and then we will retrieve this from the data broker and do the Euclidean space algorithm to match to check the similarity. It's kind of slow today. It's usually less. Okay. Okay, so everything worked. I'm glad. I'm super happy. I'm super relieved. So, uh, so we put the data. We got the data. We delete the namespace and clean everything from the data the data broker. So from the Redis server. Okay, so we are good. I'm happy. It worked almost flawlessly. So we can go back before the time expires, and I'm almost out of time, so let's go back. Demo time check. Okay. So we did some preliminary performance evaluation on the data broker. We are quite happy because we're not putting that much of overhead with our runtime. So we did two kind of experiments, a single process or just one process is that one process that is doing put and get operation from Redis, and also some parallel benchmark, and we got similar performances both on IOPS or input-output operation per second, and also from a peak on bandwidth peak. We have also similar performances, and something that we also try to exploit is doing more overlapping requests. So we're not just doing one request and block it, but we type more than one request at a time and send it to Redis. Of course, we have still some work to do on that, because we are comparing with Redis benchmark, that is a benchmark that is provided by Redis, and there is also some request pipelining that is implemented by Redis benchmark that we still don't have, so we are planning on implementing also this part, and also provide some, of course, better zero copy especially on read operations. So since I'm very late, on next direction would be trying to use Redis modules also to create like single module for multi-stage commands. We are trying and doing that right now actually, to move the Splash workflow in the cloud. So working on containerizing all the single application in the workflow, and of course also the data brokers and Redis are part of it. So we will try to move everything on the cloud. Of course, we want to do more bindings and more backends, more bindings. We will have a Java binding for the user API, and a Golang that at some point we'll have also that one. More backends. So as I said, we are also working on a hardware-based backend file system, and also memcached. Something that we're also working on is trying to use the data broker, in particular the Python interface, to try to connect also big data application like Spark, for instance, and Jupyter notebooks also, like using Spark and data broker and other like visualization tool from Jupyter notebooks in a way that we can provide a shared space with the data broker and Redis. And I am done. Thank you for attending the talk, and also thank you for Lars and Sarah that helped me to put all of this together. Thank you.